In September 2005, a swarm of earthquakes rattled the lowest point in Africa, the Afar Depression in Ethiopia. The earthquakes continued for 24 hours, and over the next 2 weeks, 163 more were recorded. This was an unparalleled geologic event, something taking place quickly and never seen before. The African continent was tearing itself apart. Just 40 years ago, a revolutionary concept, plate tectonics, changed the way we think about Earth. It helped explain Earth's most violent shudders, explosive forces, and even what gave rise to her tallest mountains. By understanding how and why the ground constantly shifts under our feet, geoscientists can show us what lies ahead.
The stresses build up, and bang, we have an episode.
Look up. Look around. Look deep below. On this episode, we explore the shifting layers beneath our feet and how they alter the faces of Earth. The unprecedented seismic event in Afar, Ethiopia, grabbed the attention of geoscientists around the world. A 37-mile fracture had ripped open in Earth's crust. At its center, a 1,600-foot-long vent, 330 feet deep. Scientists came to one unbelievable conclusion. They were witnessing the birth of a brand new ocean. Scientists rushed to Afar to monitor, in the field, what was happening. Cynthia Ebinger from the University of Rochester in New York and Tim Wright from the University of Leeds in England are members of one of the international teams.
As a geoscientist, I normally measure processes that happen at about the rate that my fingernails grow. Over a period of about 2 to 3 weeks, we had 8 meters of opening. That's about 400, 500 years worth of opening then that happened in a few weeks.
The Afar Depression was created by spreading of Earth's crust over the last 30 million years. Today, it is one of only 2 places on Earth where a spreading ridge can be studied on land rather than the bottom of the sea. The other is Iceland. What geoscientists were now seeing was clearly a result of the African and Arabian plates being pushed apart along 3 deep rifts that are called the Afar Triple Junction.
Most of what happened at depth, underneath the ground in the top 10 kilometers of the crust. So as these 2 plates moved apart, we actually had an injection of molten rock, of magma, into the crust, which allowed these plates to move apart.
Earth's outermost shell is broken into a dozen or more plates which ride atop Earth's mantle. The amount of magma that oozed in and formed this new crust in the middle of these 2 tectonic plates was over 88,000 cubic feet, enough to fill a football stadium 2,000 times over. Afar is one of the hottest and driest places on Earth. This desert has little vegetation, and any movement of the Earth is easy to spot from the air. The white bands streaking across the landscape are freshly exposed fault fractures caused by the quakes.
What we see when a fault has slipped is we'll see a dark band and then a white band at the bottom showing the areas where the dirt hasn't been sandblasted off the fault scarps. So we can go to fault scarps and directly measure the thickness of the white bands and directly measure the amount of offset.
After a 3.5-hour flight into the heart of Afar, the scientists will set up their monitoring equipment outside a small native village. The helicopter will return again at the end of the day to pick up the science team. While scientific data is important to figure out what is happening in the region, eyewitness accounts make this geologic event very human. Atalay Ayeli, one of the team members from the University of Ethiopia, has been collecting first-hand stories from Afaris living here.
Yes, definitely they were very frightened by the activity, and they were not even concerned about their goats and animals. First, they were worried about themselves. They thought that it's not going to stop.
Atalay explains to the frightened Afaris that the shaking and the changes to the land are going to continue indefinitely. They live a simple life as nomadic herders, and they live in a desert. It's not just their safety the Afaris worry about. It's their water supply. In this desert basin, the Afaris get their water by collecting it from steam vents, or boinas. Magma deep in Earth's subsurface heats the groundwater, and the resulting steam pushes up, creating the vents. But now, too much magma has risen up as a result of the rifting, and it is boiling off their available water. Atalay explains to the villagers that the recent underground activity is diminishing their water supply. They will have to find water elsewhere. One of the tasks of the scientific team is to install a permanent reference point in the rock for a global positioning satellite antenna.
Basically, we're on the axis of the spreading rift, so we're practically on the plate boundary. This is Falaka, who's a surveyor from the Ethiopian Mapping Authority. What he's doing is positioning this tripod very, very precisely on top of this benchmark down here that we've installed in the rock. At the centre of the tripod has to be above that point to the nearest millimetre, and that controls the accuracy of the measurement. It's a very delicate and somewhat time-consuming process. He's been doing it a long time, and he's very skilled at this process. Yeah. Okay, so let's see. That looks good. Nice job. Okay.
The antenna will receive precise location data from 21 satellites orbiting in space. This will help scientists chart even small movements in the Earth.
4 degrees. If this segment opens in another event similar to what happened last year, then this point can move by several meters. So this benchmark, provided it survives in this location, will be available for future scientists as well as for our own research.
The Afaris will watch over and maintain the monitoring equipment for the scientists until they return in several months. The magma is so close to the surface that it has caused Earth's crust to literally melt. Stretched like taffy, this thinned crust will eventually sink below sea level, finally giving birth to a new ocean.
And that's already started in the Danakil Depression, which goes down to getting on for 200 meters below sea level in places. In order for the water to come in, you need to cut and make a connection to the sea, and we don't know exactly when that will happen, but with continued erosion and movement of water, and the power of water will eventually find its way in.
Eventually, the salty waters of the Red Sea will breach the low hills to the east and spill across the depression, erasing traces of what is here today and has been here for millions of years. Geologists predict in about 10 million years, the whole 3,700-mile length of the East African Rift will be submerged and a new ocean will be born. At that point, Africa will have lost its horn, creating yet another new profile of Earth. Earth exists in a state of balance. Oceans are born while others die. It is happening in afar, and it happened 200 million years ago when the Atlantic Ocean was born. Why is Earth so restless? What causes the ground to shake, volcanoes to erupt, and great mountain ranges to rise to incredible heights? The face of Earth is continually shifting, influenced by a process called plate tectonics. Earth's surface, the lithosphere, is a mosaic of many plates girdling the planet like seams on a baseball. These plates drift on top of Earth's hot and slowly churning mantle, over time colliding, breaking apart, and grinding against each other. To understand tectonics, scientists look back only 200 million years, because earlier geologic evidence has been either recycled or hidden by Earth's processes. 200 million years ago, all of the continental plates we know today had collided and formed a supercontinent scientists call Pangaea. The ancient Paleo-Pacific Ocean to the west and the Tethys Sea to the east surrounded it. Soon after its formation, Pangaea began to break apart, much like what is happening in Ethiopia today. A rift opened that separated North America, Africa, and Europe, giving birth to the Atlantic Ocean. That same rift, now called the Mid-Atlantic Ridge, is still in motion, splitting Earth and widening the Atlantic. How fast is it moving? In your lifetime, North America and Africa will be about 6 feet further apart than they were when you were born. Over the next 100 million years, as the Atlantic grew and Pangaea broke up, movement of several tectonic plates closed the Tethys Sea from east to west. These collisions thrust up the great mountain ranges that we still see today, stretching from Spain all the way east to Indonesia. They also created the eastern Mediterranean Sea, the only major remnant today of the Tethys Sea. Then, around 6 million years ago, Earth's climate entered one of its many cooling periods, and ice sheets moved south from the Arctic. Trapped water in the glacial ice made sea levels fall. Combined with the collision of the African and European plates, the waters of the Atlantic and Mediterranean were separated. The collision of Africa and Europe pushed up a sill across the Straits of Gibraltar that created a barrier to the waters of the Atlantic. The water in the Mediterranean began to evaporate. During this time, the Mediterranean dried into a group of disconnected seas. Some never completely dried out, while other areas turned into dry wastelands covered with evaporated salts. This became known as the Messinian salinity crisis. Dr. Maria Sita is Professor Emeritus at the University of Milan's Department of Geology. Dr. Sita's team was the first to discover the enormous salt deposits beneath the sea floor of the Mediterranean and figure out the impact the drying out of the Mediterranean had on the rest of the world's oceans.
The volume of the salts at the bottom of the Mediterranean is 1 million cubic kilometers, which corresponds to 6% to the salinity of the world ocean. So it is quite a lot of salt trapped forever.
When the Mediterranean refilled, this salt, buried beneath sediments, did not dissolve back into the water. And this reduced the overall salinity of the world's oceans and raised the freezing temperature of seawater by 2 degrees, having an impact on the formation of sea ice.
So this is pure halite recovered in a drill site from Sicily, which are related to salt exploitation. It is so pure, this salt, that it can be used, it is just grinded.
Besides the global impact of the Messinian salinity crisis on world oceans, it also altered the climate throughout the Mediterranean, Europe, Africa, and the Middle East. It became drier and hotter. This rise in temperature may have contributed to the extinction at the end of the Miocene epoch 5 million years ago. After 1 million years, world ocean levels rose again, and the sill across the Straits of Gibraltar was finally breached, refilling the Mediterranean for a second time. It has been calculated that it might have taken as long as 1,000 years for the Mediterranean to refill. The falls that flowed over the Gibraltar Sill were more powerful than Niagara Falls today. In Earth time, the closing of the Tethys and refilling of the Mediterranean happened in an instant. Studying Earth's shifting layers deep beneath the surface is difficult not only because we can't see them, but also because the movements take place over millions of years. Scientists have discovered that Earth's movements are scalable. Slow and large-scale occurrences in nature can often be replicated on tabletop models in laboratories. Not far from the ruins of ancient Rome is the Tectonic Laboratory at the University of Rome III. Francesca Funicello has been recognized by the European Science Foundation for her geodynamic modeling. Today, Francesca is working with 2 models. The first shows what happened when the African plate rotated north into the Mediterranean basin and thrust up both the Italian Apennine Mountains and the European Alps. This is known as convergent mountain building. Francesca uses sand in this model because at this scale it simulates the same properties as crustal rock. The various layers of colored sand represent rock formations in the subsurface.
Every centimeter of sand is representative of 1 kilometer of the Earth crust.
A motorized conveyor belt generates the tectonic energy that moves one plate into the other. Millions of years of geologic time are compressed into minutes.
You can see the topography completely deformed on the top, but on the lateral view, you can see also the internal structures.
The model shows, in miniature form, the same topography found in nature. It reveals how the rock in the subsurface folds and deforms deep below the surface of Earth. The models provide a remarkable visualization to understand how many convergent types of mountains are formed.
Okay, now we will see the subduction process.
Francesca's second experiment demonstrates how ocean crust plunges into Earth's mantle in subduction zones. It's a process where an oceanic plate slides beneath a continental plate. This creates oceanic trenches and can also feed volcanoes. This process is so mysterious, this fuzzy image is the best scientists have been able to take of the actual subduction process in nature. Francesca's model reveals more useful details of how gravity pulls a plate under.
This is a plate made by silicon putty.
A slab of silicon stands in for heavy oceanic crust.
We will put this plate on glucose syrup.
Sugar syrup is the perfect substance to represent the properties of Earth's mantle.
So essentially the model is representative of the first 600 kilometers of the Earth. So the lithosphere, the first layer, and the upper mantle.
Once Francesca pushes the slab a little, nature takes its course. Time is again compressed, and we watch this plate subduct in a mere few minutes, an event that normally takes millions of years. Lasers scan the movement of the silicon plate, providing minute details of motion and dynamics. Scientists then take these findings and compare them to findings taken in the field, with seismic instruments creating a more complete picture. When colored tracking markers are added to the experiment, we can actually see how the subducting slab retreats back, causing the overriding plate to be pulled forward. This simple model is able to give scientists insight about the dynamics of Mediterranean subduction. It's for this reason that models have become important tools.
Thanks to the modeling, we can think about what happened in the past.
The dynamic nature of plate movement around the Mediterranean will eventually alter the map in this part of the world. Greece is a country in motion, and it's headed toward North Africa. The Mediterranean's volcanic eruption record is easily the longest of any on the planet. Two of the most famous incidents between humans and Earth happened here. The catastrophic eruption of a volcano on Santorini in 1640 BC is believed to have brought an end to the Minoan civilization on Crete. Some believe this eruption led to the myth of the sinking of the city of Atlantis. In 79 AD, Mount Vesuvius blew, burying the great ancient Roman cities of Herculaneum and Pompeii in 19 hours of continuous eruption. leaving an astonishing memorial of victims frozen in time. Today, the eastern Mediterranean remains just as volatile, and southern Greece is riding on top of all the action. Deep below the Aegean Sea for the past 10 million years, the Arabian and Eurasian plate have pushed into the small Aegean microplate that Greece is on. To the west, in the Ionian Sea, the African plate is subducting beneath the Aegean plate, stretching Greece west. Greece is in the process of tearing itself away from Europe and breaking apart.
Because you can see these sedimentary structures in here so well, what you consider...
Lee Royden from MIT in Boston has come to an area northeast of Athens on the Aegean at the Gulf of Evia to observe firsthand the effects of these processes in Greece.
We should go down and take a look. Okay?
From space, looking down on Greece, it's easy to see the process that is fracturing Greece apart. The successive fault lines appear as a series of north-south running lines through the landscape. However, on the ground and up close, they look very different. Only half a mile from the Aegean, Lee encounters one of the great signposts of tectonic activity in this region.
This is a really fantastic fault scarp, probably one of the best exposed faults in the world, certainly the best one I've ever seen. It boggles the mind how you can drive by this 100 times and never notice that there's this humongous fault scarp about 100 meters high sitting over here.
This is a normal fault. Normal faults are a result of the crust being stretched and then breaking into massive pieces that release tension. One side slips down, while the other block appears to rise up. In the last 10 million years, all of southern Greece has been stretched and thinned at least 6 miles across as a result of tectonic activity, creating many normal faults.
Well, seeing this for the first time and getting up close to it, what really strikes me is how incredibly smooth this surface is. It looks like somebody took a floor sander to it. You can also see up close these really nice small-scale lineations in the surface that give you the transport direction. So the upper plate just moved right down this surface, paralleling these structures here.
There is an average of a 5.0 magnitude earthquake every 2 years in Greece. During the last earthquake here, this fault pushed up nearly 20 inches. 2 hours to the west is Mount Parnassus, which was formed much earlier in time by the same tectonic processes that have created the fault near the Aegean.
This fault that we're looking at in the background is one of the faults that's accommodated the rifting apart of Greece. Down in the far edge of that slope, there's a small rounded hill, which is actually a piece of the upper plate, which belonged up on top of Mount Parnassus and has now been brought down. So there's probably at least 5 kilometers to 10 kilometers of displacement on this fault.
The plate movement that gave rise to Mount Parnassus also brought deep crustal rocks to the surface. Marble deposits, which formed several miles below the surface, were lifted up by these faults and was easy to quarry. The examples of how early civilizations used this resource can still be seen throughout Greece today. If the tectonic activity keeps flexing its muscles, scientists think that in 5 to 10 million years, southern Greece will be pulled across the Mediterranean, right up against the coast of Africa, changing Earth's face again. A volcanic eruption is one of Earth's most incredible sights. But for people living in the volcano's shadow, it is potentially one of Earth's most dangerous locations. Volcanoes are like ticking time bombs. Some remain dormant for years, while others erupt with little warning. In the past 400 years, volcanic eruptions have killed nearly 300,000 people. Today, for the 500 million people living near one of the 1,500 active volcanoes, an effective warning system could be a lifesaver. Nestled in the Alps near Geneva, Switzerland, is CERN, the world's largest particle physics laboratory, where scientists study the building blocks of matter and the forces that hold them together. One of CERN's unique projects uses high-powered computers to convert seismic readings from Mount Etna, a volcano in Sicily, and Tungurahua, a volcano in Ecuador, into audible rumbles, roars, and beeps. Literally music to the ears of these scientists. Domenico Vicinanza believes, by listening to and analyzing the variations in the melodies, that these musical patterns could warn of an impending volcanic eruption.
This is something challenging because it is the first time that people are using music as a language to describe scientific data.
The technique, known as sonification, is the acoustic counterpart of data graphic visualization.
Let Tungurahua play a piano.
Tungurahua is an active volcano in Ecuador, and its score was produced from data taken during a period when the volcano was relatively quiet. By contrast, Mount Etna's score was produced from seismic data recorded just before an eruption. What Domenico has found is that the musical intervals reflect the intensity of the seismic waves. The music is smooth when the waves are small, indicating that the volcano is quiet. The tune becomes nervous, scattering through high and low tones when an eruption is approaching. Domenico is now working to build a database of seismic sonograms from volcanoes around the world. Researchers from across Europe are helping to create the database by contributing seismic data through a public internet portal.
There are more than 140 university research centers that are contributing now, because this is a real-time picture.
Sonification is just one potential new tool that is literally keeping scientists' ears to the ground. In the future, sonification may be able to tell us when volcanoes like Etna are about to erupt. Vital, life-saving information for the 500 million people living in volcanic danger zones. Volcanoes are one of the processes that can transform the face of Earth. A very different sequence of events in the Far East built the roof of the world. Among the most dramatic and visible creations of tectonic forces are the lofty Himalayas, which stretch 1,800 miles along the border between India and Tibet. About 50 million years ago, India separated from Madagascar and began a record-breaking race to the north. Normal movement for a plate would be about 1 foot every decade. But the Indian plate was on a fast track, moving more than 29 feet in a century. The massive collision between India and Eurasia thrust up Earth's crust, forming the jagged Himalaya mountain range, and raised the roof of the world. India pushed as much as 1,800 miles into Eurasia and continues to shove north nearly 2 inches a year. This means in your lifetime it could travel 12 feet, the width of a highway lane. As a result, the Himalayas continue to grow higher. But there was a mystery afoot. Geologists noticed that 1,800 miles of India's crust was missing. Scientists had always assumed that India had slid under Eurasia, but the amount of uplift of the Himalayas and Tibetan Plateau couldn't account for all of that crust. It's only recently that geoscientists can account for its mysterious disappearance.
We can see with these tomographic techniques, we can see where it has gone.
One of the ways geoscientists like Rob Vanderhilst of MIT solve the mystery is by using seismic data to generate images called tomographs.
Seismic tomography is a technique for imaging the deep earth that was adopted from medical imaging. CAT scan imaging, MRI imaging, X-rays. Well, with seismic waves we do the same thing. We had an array of about 50 stations that we operated for about a year to get additional data for high-resolution studies in that particular region. So there's about 100,000 seismograms that we actually use to construct these images.
This tomographic image exposes a 1,000-mile thick slice of Earth's interior. The blue represents faster-moving material in Earth's mantle. In this case, the Indian plate. Red indicates the warmer and slower-moving material of the Eurasian continent. Here, Rob's image reveals the missing material of the Indian plate bending back on itself.
So with the combination of, say, these tomographic techniques and what we know from plate reconstructions and geology at the surface, we can really begin to understand how this system has changed over time. So this helps us greatly to understand how India has interacted with Tibet and what actually has been driving the Tibetan Plateau.
The continuing collision of the Indian and Eurasian plates makes this region of the world very prone to earthquakes. On October 8, 2005, a 7.6 earthquake shook the Pakistan-administered region of Kashmir on the border with India. It killed 90,000 people, maybe more. There is also another region of potentially deadly tectonic activity on the west coast of California. With every tremor and jolt, the question is asked, is there a way to create an effective warning system? It's just another sunny day in California. What could possibly go wrong? The San Andreas Fault. Even though California experiences 10,000 earthquakes every year, most of them are not felt by California's 33 million inhabitants. Only a handful are strong enough to get their attention. The 800-mile-long San Andreas Fault is perhaps one of the most worrisome examples of human tectonic interaction. The boundary of the fault is formed by two plates which move side by side, periodically building up tension. The Pacific Plate on the west and the North American Plate on the east. When the tension is finally released, the landscape shakes and shudders. The United States Geologic Survey Center in Golden, Colorado, monitors global earthquakes in real time. The center pinpoints 12,000 to 14,000 earthquakes around the world each year, about 35 per day. David Wald is a seismologist at the center.
Within a few minutes of an earthquake in the U.S., within tens of minutes around the globe, we can determine the size of the earthquake, the magnitude and location, and from that estimate what the impact is going to be in that area.
The USGS has an extensive network of seismometers keeping a watch on the San Andreas Fault. When an earthquake happens, data is gathered from the seismometers to create a shake map. These maps show the level of shaking in specific areas within 5 minutes after an earthquake.
There's a number of different uses of a shake map. One of them is just emergency response and understanding the scope of the disaster.
Another use of these maps by federal, state, and local governments is to create pre-response plans based on existing information. For example, they are an important tool used by the California Department of Transportation, which is responsible for the 12,000 overpasses in California. After a large quake, shake maps can create an overview of the affected area, showing where overpasses may have been damaged. In the event of a future earthquake, these maps could tell repair teams where to head first. Shake maps created from present and past earthquakes are also useful for future construction and determining appropriate building codes for an area that might be prone to shaking. But trying to figure out where and when an earthquake might occur is tricky. Richard Allen with the University of California at Berkeley is developing an early warning system using the seismometers stationed around the San Francisco Bay, just like this one in the Berkeley Hills.
So we're now at the very back of the seismic vault for about 20 or 30 meters underground. These are part of the network in Northern California, and we're using all of those instruments to start to test whether we can do earthquake early warning.
In 1989, San Francisco's Loma Prieta quake and the 1994 Northridge quake in Los Angeles killed 100 people and caused nearly $40 billion in damages. Yet Californians have a way of rolling with the punches.
The earthquakes that we're familiar with, the Northridge and the Loma Prieta earthquakes, really are very small, fairly insignificant events when it comes to geologic processes. So it's these big earthquakes, which we haven't really seen, that the earthquakes we're concerned about.
Efforts at earthquake early warning are going on around the world, in Japan, in Mexico, and in Taiwan.
Here in California, it's a little different. We actually have millions of people living right on top of the fault. We need to really push the envelope and really minimize the amount of time that we need in order to get this warning out so that we can provide warning even for people who are very close to the fault.
The idea of early warning is to rapidly detect the first tremors of an earthquake. P waves, or primary waves, which are yellow, are the fastest of all seismic waves and are the first to arrive at any seismic station. The red shear waves travel more slowly. They are the most destructive type of seismic wave generated by an earthquake.
We're talking about a few seconds of warning, first of all, so we're talking seconds to tens of seconds. What you can do with that kind of time is you can start to slow and stop trains, and so there's less chance of the train derailing. We can stop planes from landing at airports. If we have some particularly sensitive highway structures, such as bridges, we might actually start thinking about slowing down traffic and actually stopping traffic from entering bridges.
To the people in Los Angeles in 1994, this kind of warning might have made a difference. The San Andreas is going to continue to move northwards and is sure to generate more earthquakes for California. The Los Angeles section of the San Andreas Fault is moving north faster than the San Francisco section. In 10 to 11 million years, Los Angeles will become a suburb of San Francisco. The power of tectonics is responsible for the look and shape of everything that makes up our planet. After billions of years, the same incredible force of energy that churns deep inside can rip Earth apart, erupt with unpredictability, move a continent, and even create a new ocean. There is no one face of Earth. Because of the constantly shifting ground beneath our feet, there have been and will always be many faces of Earth.